Okay, again, when I created this activity, this is an activity that I taught for my in-class and my hybrid classes, not my online class, but because all classes are online now, I wanted you guys to get the same experience. So what happens in the classroom? In the classroom, there's a graphing board. It's in every single math classroom in our building. And there's a graph board that just has, a traditional X and Y axis, and it has the center of the X and Y axis, so there's the center line there, there's the center line there. And you can go and you can graph things like y equals x squared, and it's just like graphing it on a calculator, right? You can see it, and then teachers can use this graph board on the calculator, on the graphing board on the wall to more accurately and to scale draw these graphs. Now, the important word that I said there is to scale. Because when we graph things in mathematics, when I teach an algebra course, I'm like, okay, graph x squared, and you'll see me graph y equals x squared. It'll look like that. This is not to scale, and it's a very small snapshot. So the question is if we zoom out, what would this actually look like? Okay, how far does it actually climb? I mean, I see the climb, but how steep am I actually climbing? Well, I want you to compare exponential functions to get an idea of what would this look like. So when we did the last problem, the penny problem, the penny was doubling every single day. And I talked about this and I said, what about something like COVID? Is it realistic to think that something doesn't double every single day, that something realistically could potentially even triple every single day? And the answer is yes, it's very conceivable that this can happen. Maybe, again, not something like COVID. Diseases would be very, very scary if they were tripling. But there have been diseases that have been spread at rates of tripling, like back in the days of plague and such. So let's model if something tripled. And what we wanted to do was, if we had that graphing board on the wall, I wanted to graph what would it look like if we were looking at, we said the number of pennies was 2 to the number of nights. Well, what if we did 3 to the number of nights? And let's graph that on the wall, and let's graph it accurately. And so what's the idea? When I look at that graph, I would start off the graph with just a 1 there, right? And this would be day 0. I would have 1 penny, or 1 person would be sick. And then after 1 night, it wouldn't be 2 people would be sick now. So this would be the 0.01. The next one would be the 0.13. And then the next one would be the 0.2. And then if that doubled, if that tripled, because we're tripling every single time, now it'd be all the way to 9, right? So there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'd be at 2, 9. Is what I'd be if I tripled twice. That's what I'd be at. So then I'd be at 3, and then what would I have to go to? Well, if you already notice, 9 times 3 is 27. So what's the problem is I go so steep that I'm off the board. And my question then became, if I wanted to graph this accurately, I have all these X tick marks over here. If I went all the way over to this last X value, the question is, how high would I have to go to graph it accurately? So there's some things that you need to know about this graph board that you don't even know how many there are. You don't even see the graph board. So what was the graph board? The graph board on the wall, and this is the point in time when I would literally get out the yardstick and I'd measure the squares. The idea was there are 22 squares across the bottom, and each square is 2 inches long. 2 inches. Okay? So the question is, if I went over to square number 22, how high would I have to go? Okay. Well, the first thing that I wanted to determine was how many squares do I actually need to go up? Well, this is 22 nights and I triple every single night, wouldn't I need 3 to the 22 squares? I would need 3 to the 22 squares because it's 22 times of tripling. Okay. Let's keep on going here. If I have 3 to the 22 squares, and I know how big each square is, don't I? 1 square is 2 inches. And then I want to convert this to feet. I know that there's 12 inches in 1 foot. And I want to go further. Let's convert it into miles. I know that there's 5280 feet in 1 mile. So now I've gone from how many squares do I need to go up to how many miles do I need to go up. And again, remember, I've only gone over 22 squares at 2 inches a square, so that would be 44 inches, which is approximately less than, it's less than 4 feet. So the idea is if I wanted to graph this, from the starting point, I would go 4 feet to the right, not even 4 feet to the right, 48 inches is 4 feet. So I'd not even go 4 feet to the right. How high up would I have to go into the sky to plot this point to scale? That's the number that we're going to figure out. So in my calculator, I'm going to do n over d. I'm going to go 3 raised to this 22nd power. I'm going to multiply that times 2. In the denominator, I'm going to do 12 times 5280. I hit enter, and what's the answer? The answer I'm getting is 990,563.75 miles. I would have to go almost a million miles into the air to graph that point accurately on that board in the window. So if you can picture a board on the window, I start in the bottom left corner of the graphing board. To graph this accurately, I would step not even 4 feet to the right. I would have to go almost a million miles straight up into the air. So again, how high is a million? Well, I Googled how far is the moon from the Earth? Go ahead and distance it. How far is the moon from the Earth? I'm getting a total of, right now it's 238,000 miles. Okay, that changes, right, depending on where we are in the time of year and such. But right now it's about 239,000. So I'd have to go pretty much 4 times the height of the moon to graph that point accurately. Exponential growth is extremely scary. If you don't stop it, if it's not naturally contained, if you don't quarantine it, it can wipe out entire populations, or at least infect entire populations. These ideas of exponential growth are scary real. And that's what I had you look at the next one. It says, so a leprechaun and a magic penny doesn't seem like a likely scenario, but does exponential growth really exist? Can anyone think of real-world things that see exponential growth patterns? I will let you know I lectured this section 2 weeks before COVID broke out. 2 weeks I did this exact lecture saying you need to be afraid of exponential growth. It's very scary. And the next thing we see, we go on spring break and we come back and see exponential growth in a national disaster, not a national, a worldwide disaster, a pandemic with exponential growth. So I hope this section, again, there's no homework for this section. There's no quiz for this section. I wanted this section to be enlightening. I wanted you to see what large numbers really are. I wanted you to see what exponential growth is. I wanted you to see what these models are when you see these curves. When you see COVID happening, when you see the growth rates, and you see something going up like this, if that pattern continues, we're all infected and or die. So we had to curve it, and we had to go into quarantine so that growth stopped, and you hope that it starts to go back down, but it's not going to go down near as fast as it went up. That's our hope as to what the curve can look like. We'll see if that's what actually happens. I hope you're all staying safe, and I hope you enjoyed this section. Thank you for your patience in listening to these videos.